So what will be the charge? Tell. See here. This is a cell. Outside concentration is 110. Inside is 11. So to be equilibrium, what will be the direction of the charge flow? So direction will be outside to inside. So this is potassium ions, chloride ions. Okay, so we will see that the charge moving inside will be negative, more negative. So the charges will be minus 60 millivolt. If this will be opposite, if 110 will be inside, just say if 110 will be inside concentration and outside will be 11, then the net movement will be outside, so inside will be positive. So negative charge moving outside, so it will be positive. I told you before only, all this membrane potential chapter we have to see everything with respect to the membrane. Okay, inside the membrane, inside the cell, we have to see inside the cell all the charges, everything, positive, negative. Why we have to see inside the cell? Okay, a cell is there. Let's say one cell is there and it is covered with the membrane. Outside will be the interstitial region. So how we can we can't define with outside until unless we will see from inside. So inside we have to focus more in this chapter. Okay, how I told in hypokalemia and hyperkalemia, like the charges of the concentration of the potassium in the case of hypokalemia will be less inside. Okay, and in the case of hyperkalemia, the concentration of potassium will be more inside. So all the time we have to see the inner cell concentration. Like that, in the question given, 11 millimolar concentration is inside. So to be in equilibrium, so it has to move inside from outside concentration more. So that's why the chloride ion is there. So negative concentration increases inside. That's why it is negative. Okay. Now we will see the next equation, that is Goldman. Okay, so I already told you if the more than one type of charges is there, in that case we will use Goldman equation. For Goldman we have to see two parameters. One is concentration of ions. Okay, more than one ions there. Second, the permeability of the ions. So on this basis we are going to find the Goldman equation. Please do remember these two parameters. Just say this is the outside, here is the inside. Inside potassium there, chlorine there, sodium there. So these three charges can go to and fro easily. This is inside. Okay, here is outside, it can go and come out. But in the case of protein, we all know that at high pH the protein is negative. So negative charge protein, it can't cross since it's a macromolecules. So what will happen? There will be disturbance in the permeability of the ions. Okay, and this is known as Gibbs-Donnan effect. Please do remember, most recently this question was asked in NEET exam, NEET PC. Gibbs-Donnan effect. What is this? The disturbance in the permeability due to negative non-permeable protein. Okay, the disturbance in the permeability due to non-permeable protein which will not which will disturb the movement of other permeable ions. Okay, so what I told, in the Gibbs-Donnan effect, the disturbance in the permeability, okay, and which is due to non-permeable protein, negative non-permeable protein, okay, and that will disturb the movement of other permeable ions, means like sodium there, potassium there, okay, then here sodium, potassium, this is inside, this is outside, and inside the protein also there, negative charge protein. So of course this protein will disturb the concentration gradient as permeability as well as concentration. So this is Gibbs-Donnan effect. So there are some consequences of the Gibbs-Donnan effect. First is consequences. First is let's say a negative charge, negative protein here the outside. So this is sodium here. What it will do? It will attract sodium inside the cell, and with the sodium a water molecules will come with it. So this is the membrane. With sodium, water molecules also come inside it. Okay. So how many sodium will go with the sodium? Water molecule attached with the sodium, it will come, and what will happen? The increase in the size of cell due to turbidity. So what will happen? What you are thinking? The cell will be burst. In that case, tell. No, the cell is not going to burst. So see what will happen. With the help of sodium potassium ATPase, sodium potassium ATPase, it's an enzyme which will open the sodium potassium channel and water will go out and potassium remain inside of the cell. Okay, so what is happening? Negative charge protein, it is attracting sodium plus water is coming with it. Okay, and the cell size increases. Size increases. After that, with the help of sodium potassium ATPase, again the water is coming out. Water is coming out and the cell become again thin. Okay, so this is happening. This is the first consequences. I gave you shortcut, I told you here, so remember. Second is the oncotic colloidal pressure. What is this oncotic colloidal pressure? You know what is oncotic colloidal pressure? This is the osmotic pressure. The osmosis will happen. Okay, the osmosis will happen. Where osmosis will happen? in the capillaries vessels. Okay, and what will cause it? What will cause? Here also I told you protein, because we are seeing in Gibbs Donnan effect, basically the protein is the main things. Okay, so the protein is the leader here, and you know what is a protein? That is albumin. And we already studied albumin is a protein which is going to maintain a blood pressure in our body. See what will happen in the oncotic blood pressure. Just say this is a capillaries. Okay, here is the interstitial region. Here this is a protein albumin. So we know that albumin will work as a solute here, and there is an interstitial region, and since interstitial region, interstitial fluid will be there. Interstitial fluid will be there. So we know that osmosis, always a movement of water from the region of higher concentration to the region of lower concentration inside the capillaries. Inside the capillaries, blood also there, and in the blood we have a water. Which segment of blood is water? The plasma. Okay, in plasma the most component is water, that is more than 95%. Okay, so here just say water is there. Okay, in that protein also there. So but the water amount is less due to presence of protein, and in the interstitial region the water is more. The water is more on the both side. Okay, so what will happen? The osmosis occur, and due to osmosis the inward movement of water will take place. This will increase the fluid inside the increase the fluid inside the capillary or the blood vessels. Okay, so this is the oncotic pressure, and always remember oncotic pressure is always opposite of hydrostatic pressure. This pressure is coming with the blood, and if the blood is having more water, so what blood will try to do? It will try to force outside water. Okay, blood will try to force outside water, means outside in the interstitial region. Okay, so this will happen. Always hydrostatic pressure is opposite of oncotic colloid pressure. Okay, so why we say colloid? Because of presence of protein, that is albumin. Albumin here. Okay, so this is there, and the last and the third consequences is, the third is the inside the cell. Now last and third, inside the cell the charges are negative more due to presence of protein mostly. Okay, but do remember, protein can be negative as well as positive. When it will be negative? When the pH is high, that is above 7. Okay, in that case it will be negative. Okay, this is done. This was all about the Gibbs-Donnan effect. Please remember, because most of the time the question has been asked from here. Now we are going to see the action potential of neurons. In the action potential, we are going to study the polarization, the latent phase, local potential, depolarization, all these in detail. We are going to see which ions is going to enter inside the cell, which is going to exit or efflux outside the cell. So we all know that the resting membrane potential of nerve cell is minus 70 millivolt. So in the action potential, first I will going to draw one graph. This is a graph of action potential. This is minus 70 millivolt. We are going to see, okay, one by one what all. Okay, in y-axis we are going to see the potential. In x-axis we are going to see the time. So from we can see that after a stimulus is generated, the time gap between the stimulus and the response to start is known as latent phase or latent period. What is latent period? What is latent period? The duration between a stimulus and response. So this is the time after putting the stimulus. So this is a time taken for response to start. So initially the cell is in resting membrane potential. Here minus 70 millivolt. This is a resting membrane potential. After a stimulus generated, the cell started getting exciting. So the first phase is local potential. Local phase, local potential. So what is local potential? This is, we can say, the threshold potential, the minimum potential we required for the action potential to start, or the minimum potential which begin the action potential. This is a local potential. So in the case of local potential, the sodium ion influx inside the cell, what is going to happen? But these sodium ions which is going to influx inside the cell, it is very steady, very slow. Okay, slowly, it's because the cell is going to attain the threshold after the minimum potential which required to start the action potential. This is the local potential, we can say it. So that is the potential, the resting membrane potential, which is minus 70 millivolt, going to change minus 55 millivolt for the nerve cell, and this is the threshold potential. Here it is minus 55 millivolt. So after that, the next is depolarization phase. What is depolarization phase? In depolarization phase, the influx of sodium ions will be increased, and the speed of sodium ions coming inside the cell is more getting high and high, and which will make the cell to be positive, inside the cell to be positive. So the influx of sodium ions will be very high, which lead the potential of the cell to be positive, and that reaches to minus 35 millivolt. So this is the potential while depolarization. We have already shown that the depolarization phase is the first starting phase for action potential, or you can say is the first phase. Of action potential. So we can see here the increase in the membrane potential till plus 35, sorry, it should be plus 35, not minus 35, plus 35 millivolt. Okay, then after that, the second phase, which is followed by depolarization, is repolarization. In the phase of repolarization, the efflux of, or the moving out of potassium ions outside the cell and cause the inside negative and it will again take the potential to minus 60 millivolt. Again I will draw this. So this is first phase, that is local potential. After that this is a this is the first local potential. Next depolarization. Now again in repolarization the membrane potential again decreasing and it reaches to minus 65 millivolt. After that it will not stop, it will come again down and then it is going to increase and attain the resting membrane potential minus 70 millivolt. This is potential, here is the time. So after depolarization the next phase is hyperpolarization. What is hyperpolarization? In the hyperpolarization the cell or the nerve cell will be in the inhibitory phase, which is the nerve cell is going to inhibit or antagonize something, that is. And what causes the hyperpolarization? Influx of chloride ion and efflux of potassium ions. This is the main cause of hyperpolarization, so please do remember this. So if the more and more chloride ions will enter inside the cell, so cell will be more negative and the efflux of potassium ions will also cause the inside cell will be negative. So this is a case of hyperpolarization. And when the cell or nerve cell is in the hyperpolarization, it means it is going to inhibit something. So what is a neuroinhibitor? Some of the neuroinhibitors are dopamine, and GABA. Gamma amino butyric acid. This too is a neuroinhibitor. Okay. So this was all the phase of repolarization. Now we have a term that is refractive period. Now we will see refractive period. Always remember this refractive periods is always with respect to new stimulus. So whenever new stimulus will come in the middle of the action potential, so that will be the refractive periods. Refractive periods basically has two types. One is absolute refractive periods, and the next is relative refractive periods. So what is absolute refractive periods? In the absolute refractive periods, remember, it is between the threshold potential which is minus 55 millivolt to 1/3 of repolarization. So this is a absolute refractive periods. So in this period, if any new response or any new stimulus is going to come, the nerve cell is not going to take it, or that stimulus can't be produce other response. Okay, so it doesn't matter how strong is the stimulus, but it can't make the response. But in the case of relative refractive period, that is from 1/3 of repolarization to the whole of action potential. If new stimulus and the strong stimulus is going to come in this period, so of course it is going to produce a new response. So this is a relative refractive period. But please remember, the new stimulus should be strong. It should not be weak. It should be strong stimulus. It will produce response. With new stimulus. Means the action potential is going on. Just say that one stimulus came and the action potential is going, and in the between of the action potential, just say if the action potential is between the minus 55 millivolt and in the polarization phase, sorry, not polarization, depolarization phase. So in that phase, which is from here to here, if during this period, if any new stimulus will come, it doesn't matter how strong is the stimulus, if any stimulus is going to come, it will not produce a new response. That stimulus can't produce new response. But after this 1/3 of repolarization till the last, sorry, here till the last, a new stimulus can produce a response, but it should be strong. The weak stimulus can't generate a new response. So this is a refractive periods. Yeah, so we have a new question here. We have a question here. The membrane potential is plus 22 millivolt. Can a new stimulus with high potential will generate the response? So this is a question. So can it produce? What will the answer? Yes or no? Yes, it's no. Why it's no? Because here this 22 millivolt, this is a period of depolarization. So of course the depolarization periods can't make a new response for any strong, whatever will be the potential of the stimulus, it can't make the response, whatever. But if this potential will be like minus 50 millivolt, in that case yes, it could make, because minus 50 millivolt, this is a phase of repolarization, so in that case it can make. But here the question is given the membrane potential 22 millivolt,